this section we want to talk about relation between the sufficient statistics and complete statistics. There are important theorems which explain this relationship. It's called the Boswell theorem. In fact, it is the theorem 4.1. It said let's X is a complete minimal sufficient statistic. It is independent on every ancillary statistics. So, if the minimal sufficient statistics is complete, then Tx is independent every ancillary statistics. The proof is given for discrete distribution, only for discrete distribution. Let Sx be the ancillary statistics, and then the distribution of Sx is not depend on theta, because as a definition of the ancillary statistics is that there's distribution is not depend on theta. So we can write the conditional distribution property Sx equal S, condition on Tx equal T is equal the X is the definition of the conditional distribution. This property does not depend on theta because T is X is sufficient statistic, and the distribution of any statistic conditional of sufficient statistic and does not depend on the theta. So we want to show Sx and Tx are independent. It is sufficient to show probability of Sx equal S, condition Tx equal T is probability Sx equal S is a definition of independence and random variables. Consider first probability of Sx equal S. You can write by using the probability conditional probability distribution probability Sx condition Tx at probability Tx equal T. But Tx is a random variable, so all the summation of all value of that is equal to 1, and we have Sx equal S is equal to probability Sx equal S produced in the Tx equal T, because this part, the first part, is not depend on T. Can draw out, and this summation is 1. So if we define Gt equal probability Sx equal S condition Tx equal T minus probability Sx equal S from two equation, if we use two equation, we have expectation of Tx equal Gt probability Tx equals 0. Because Tx is the complete, if expectation Gt is 0, then Gt is 0 with probability 1. Hence Gt is 0 with probability 1, and we can find probability S equal S. If this that one is equal 0, we find this one. So the random variable Sx and Tx are independent. For the continuous case, we should show that the conditional density function of S condition on T is equal the unconditional distribution S, or that Fs equal Fs condition on T. We consider a statistic phi TUS Fs minus Fs conditional on T. As you see, this is function of T. Okay, this is the function of T. We calculate the expectation phi Tx. We can find that one. This is a distribution of only T is a random variable, and we have with the replace phi T, we find that one. Okay, and in this part, if it is a constant value corresponding to random variable T, and you can find that equation Fs minus expectation Fs conditional T, and this is a function of T. Then you can write as a function of T here is Fs minus Fs condition T, that Ft for the dt. This is a joint distribution of Fs and T. So when integral out of the joint distribution, we find marginal distribution Fs. So Fs minus Fs is 0. Therefore, expectation of phi Tx is equal to 0. And because the T is the complete sufficient statistic, phi T is 0 with probability 1, and we have this equation Fs equal Fs conditional T. So we have if T is complete sufficient statistic, it is independent as every ancillary statistics. For example, let x1, x2 to xn be IID random variable from the uniform 0 and theta. Then Tx equal xn is complete sufficient statistic for theta, and we can find xi divided by theta is uniform 0, 1, and this distribution is not dependent on theta. So xi divided by xn order, we can write xi divided by theta, xn divided by theta, and this distribution xi divided by theta is uniform 0, 1. So the by the definition of xi divided by theta, xn ordered divided by theta has distribution independent of theta. So the numerator and denominator distributions are independent as theta. So xi and xn is divided by theta. Divided does not depend on theta. Then xn and x1, xn order is independent by the theorem. We have another definition for complete statistics. We set T is complete statistics is if the expectation gt is equal to 0, we have gt is 0 with probability 1. When you define the complete statistics, we does not put any condition on the function g, but if this property is satisfied when the g is the bounded distribution, we call it bounded completeness. So let f theta is a formula probability distribution with induced by some statistics t. We set t is the bounded complete for theta if for the any bounded real function g. I have this equation. The only difference between boundedly completeness and completeness is this property is satisfied only for bounded distribution. So if t is complete, is boundedly complete. Okay, because when you say t is complete for every function g, this equation is satisfied. But the inverse is not necessarily true, because if this property is satisfied for the boundedly complete, is not show that it is satisfied for every function. So the complete statistic is boundedly complete, but the image is not true, not necessary. There are example here. Is a classical example. Consider x as a discrete distribution as follows, with the x for x equal -1, this density equal to theta, and for x equal 0, 1, 1, to infinity, the mass function, probability mass function is equal is 1 minus theta square, theta power x. We can show the x is the boundedly complete, but x is not complete sufficient for theta. Is that proof of that? You can look it and prove, and you can find so another theorem. It is important for the relation between complete statistics and sufficient statistics, is that if a sufficient statistic is boundedly complete, it is minimal sufficient statistic. Okay, if t, for example, t is sufficient and complete, boundedly complete, and it is minimal sufficient, is one way to find the minimal sufficient statistics. If you look for the sufficient statistic, it is boundedly complete, it is minimal sufficient. Only not that if the sufficiency is complete, it is boundedly complete. Therefore, this condition, boundedly complete, is vector of complete. So, for the proof, let Tx is the boundedly complete sufficiency statistic and Sx is other sufficient statistics. We show that Tx is the function of Sx with probability 1. By the definition, Tx is minimal sufficient statistic. Tx is function of every sufficient statistics. Okay. Let G be a bounded real value function. We define Hs by the expectation Gt conditional on S, and Lt is expectation Hs conditional on T. Then if you use of the condition expectation of Hs equal expectation, and expectation Gt conditional S is equal by the expectation Gt, and so that expectation Lt is equal expectation Hs conditional T is equal to expectation Hs, and we have the expectation Hs. So we have this equation: expected Hs equal to expected Gt equal to Lt, and you can find this non-equality between the Lx, Tx, and variance of Lx, Tx, and Lx, Hs, and Gt. We can show that the variance of Hs by the definition is equal to expectation variance Hs conditional on T plus variance of expectation Hs conditional T. Or by the definition is expectation Hs conditional on T is Lt. So we have this part. As we know, variance is a positive function, then expectation of positive value is positive, and this expectation of positive, there it is greater than variance of Lt. Similarly, you have variance of Gt is equal to expectation variance of Gt condition S plus by variance of Hs, because this is a positive value, and so we have this non-equality. So for this equality we have expectation Lt minus Gt, Lt minus Gt, expectation of that one is 0, because Lt and Gt is the function of the T, and T is boundedly complete, so Lt minus Gt is 0. It's from the definition of the complete sufficient statistics. So we have Lt equal Gt with probability 1 when T is the boundedly complete. Okay, therefore this non-equality should be equality, and Gt is equal Hs with probability 1. It means that every bounded real value function of T is the function of S with probability 1. If T is the bounded, S is the function of T. Okay, because you know from this equality we have S equal H inverse Gt. So if the T is the bounded, and S is it is function of S with probability 1. If not, we can find Gt by Gt which which is bounded with probability 1. For example, I define the gt equal 1 and divided by 1 plus e beta on t. In this case, gt is the bounded function, and gtx is the function of s with probability 1, and s is the function of probability 1, and then ti is a function of s with probability 1. So t is a function of s with probability 1, so t is the minimal sufficient statistics. So we have here some important theory. We can use it in this part and show the relationship between sufficient, complete, and minimal sufficient statistics and ancillary statistics. The first one is the Bosso theorem. Said Tx is a complete sufficient statistic, then Tx is independent on ancillary statistics. So in this one, as we have uniform theta and theta plus 1, we find the part of this minimal sufficient is ancillary, so the distribution uniform theta and theta plus 1 is not the x1 and xn is the minimal sufficient statistic, but is not complete. In is the theorem, you can use it to show the completeness and minimal sufficiency and ancillary. The second one is a theorem. Is show the relation between the sufficient statistics when the sufficient statistic is bounded is the minimal sufficient statistics. Is we can extend it to if t is complete statistics, bound sufficient complete, it is minimal sufficiency. Is one way to find the minimal sufficient statistics. So the proof of theorem is not used in the exam. Actually, we only use the theorem. It's not the proof. But the proof here can be used, the method of the proof in the proof of the theorem. In the next section, we tried to define a special family of distribution. In this family of distribution, as called exponential family, you can find minimal sufficient statistic, complete statistic, and other types of the distribution as a special form, which is useful in statistical inference. Actually, the applied statistic is the best of the exponential family distribution. So the exponential family is very important in statistics. We only look for the density sufficient statistic and other property of the exponential family we can find in different books about the inference